In lesson 114, you'll be learning about the exponential key on a calculator, and then we'll also be talking about exponential growth and using your graphing calculator to graph exponential functions. First, let's learn about what the exponential key is. Now, if you had this relationship here, 4 to the exponent of 2, that superscript or that 2, that's called an exponent, and we've worked with numbers like that, and we know that that would just be 4 times 4 is 16. Now, if you had this, 4 to the 9th, now that's going to be a little bit more complicated, and you just multiply 4 by itself 9 times in a row, and that would take quite a while. But using a scientific calculator or a graphing calculator, it makes that process a whole lot simpler. So let's look at a graphing calculator and a scientific calculator and see how to calculate 4 to the 9th on both of those. Now, I don't think it's critical that you have a graphing calculator to do Algebra 1. You probably want to get one for Algebra 2, though. The one I like to use is the TI-83 Plus. Now, your graphing calculator may work differently than a TI-83 Plus, but let me just show you how to figure out 4 to the 9th on a TI-83 Plus. First, you hit the 4, and you can move up and you can see that there's a 4 on the screen at the top left corner. Next, you hit that little upside down V. It's called a chevron mark. That's the exponent key, and that tells your calculator that the next value after that will be an exponent of 4. So you can see it. It's not the best picture, but you can see that little chevron mark right after the 4 on the screen. Next, type in your exponent. In this case, we want our exponent to be 9, and so on the screen you should have 4 to the power of 9, 4, a chevron mark, and 9. That tells the calculator that you're doing 4 raised to the power of 9. Then you're ready to make the calculator solve for that exponential relationship, and so you hit the enter key and you go up and you see right here, here's the answer, 262,144. So to solve an exponential type problem on the graphing calculator, for this one we typed in a 4, then the chevron mark, which is the exponent key, 9, and then we hit enter, and that gave us our value. Now let's figure out the same problem using a scientific calculator. One reason I say don't worry about getting a graphing calculator now is because they're pretty expensive. TI-83 Plus is around $100. A graphing or a scientific calculator like this one here is $10 or less. So if you don't have a scientific calculator, you should at least get a scientific calculator. To solve 4 to the 9th on a scientific calculator, first you type in a 4. Now, not all scientific calculators are the same, but for this one, to tell you or to make the calculator know that the next value you're going to type in is an exponent, you hit that X to the Y key. And so you press that, but the 4 still stays up there. The 4 doesn't go away until you type in the value you want for your exponent. And so you hit the 9 key. Then on this calculator you hit the equal sign. Remember, on the graphing calculator you hit the enter button. Now just to the left of that equal sign it says EXP. You might think that means the exponent key as well. What that is talking about is scientific notation, and we won't worry about that right now. So when you hit the equals button, then the value comes up on the screen, 262,144, just like we got on the graphing calculator. So for this particular scientific calculator, you hit 4, the XY key, 9, and then the equal sign. And that brings up your answer, 262,144. Well, now let's go ahead and do a few practice problems. Practice problem A is 2.5 to the 3rd power. I want you to simplify that. So if you were using a graphing calculator, you'd hit 2.5, then your exponent key, which is that chevron mark, 3, and then you'd hit enter. And once you write these answers to 3 or 4 decimal places, and this one would be 15.625. Now you could multiply that out. It would just be kind of a pain to have to do that. That's why we use a graphing calculator or a scientific calculator. Now, a scientific calculator really comes in handy on a problem like B, 3 to the 4.1 power. So what we would do there is just 3, hit our exponent key, whatever that is, 4.1, and then enter, and round them to 4 decimal places, 90.4060, because it'd be 59771, 4060, or just 90.406. And then the last one there, 4.2 to the 0.5 power, you just type in 4.2, hit your exponent key, 0.5, enter, and you get 2.0494 as an answer. That would round up to a 4 at the end. Now, part B of this lesson is on exponential growth, and there are a couple of functions that we can use that deal with exponents. One of them is called the exponential growth function, and a function, we can write that a of t. Instead of like f of x, we just say a for amount of t, and t is dealing with time because we're talking about something growing over time. And that's equal to an initial amount, and we call that a subscript 0 because 0 stands for at time equals 0 at the beginning. So that's what the a sub 0 means. And then we'll use a variable y to the power of t, or the exponent t. Now there's also another kind of exponential growth function. This one deals with the growth of money. For example, if you were saving money in a bank at a certain interest rate, they might use a formula similar to this, where we can still use a of t, some amount at time t, equals an initial amount of money times 1 plus r. R is the interest rate, and then that will be raised to the power of t. So that is an exponential function as well. Now notice the exponent is a variable now. Think about our other functions that we know they're graphs for, like a cubic function or a quadratic function or an absolute value function. All of those, the variable was not an exponent. Now in exponential growth functions, the exponent is the variable. The a sub 0, the a naught, sometimes it's called, like NAUGHT, that kind of means 0. A naught is a constant value. Y, that's going to be a constant as well. And so is R. R is an interest rate, a percentage. Y is called the growth multiplier. For example, if you were looking at a population that's growth was doubling every hour, you would use a 2 for the Y value, for the growth multiplier. If it was tripling every hour, you would use 3 for the growth multiplier. So that first function, at equals a naught y to the t, we'll consider that our growth function, our exponential growth function. The second one, let's consider that our interest function. Let's go ahead and do a couple of practice problems dealing with these exponential functions. Practice problem D says the number of weeds doubled every week. If there were initially 11 weeds, how many weeds were there after 4 weeks? Well, we see that that's an exponential growth relationship there. And so we write down our formula. A of t is equal to a naught y to the t. And let's just go ahead and substitute in there what we know. The number of weeds doubled every week. So that tells us that our growth multiplier is 2. And initially there were 11 weeds. So we'll say 11 times 2 to the t. Now, we want to know how many weeds there were after 4 weeks. So we're saying a of 4. And it's important that you keep your time units consistent throughout. This equation, or this relationship here, is discussing what's happening during a week's period of time. The weeds double every week, so we wouldn't be able to do a function here based on a daily rate, because the doubling was given to us how that occurs every week. So now we would have a of 4 is equal to 11 times 2 to the 4th. Okay, so we should do 2 to the 4th first. You can do that on your calculator, or maybe you already know that 2 to the 4th is equal to 16. So, but do that first. Do the exponential part separate from the 11. So the part that I'm circling there, calculate that separately from the 11. 2 to the 4th, that's just 16. So we'll have 11 times 16. And now you can go ahead and figure that out. 11 times 16 is equal to 176. So that's how many weeds there were after 4 weeks. We'll just say 176 weeds. And so that's the answer. Let's do one more problem. Been given that we have a $1,000 amount to deposit at an interest rate of 5% compounded annually. And what I want you to find is the dollar amount after 7 years in the bank at that interest rate. Now when you see those words compounded annually, that's a key to tell you to do the interest formula. A of t is equal to A sub 0 times 1 plus the interest rate to the t power. So those words compounded annually tell you to use that function. What that means, compounded annually, that means that the interest rate is added on at the end of each year. So let's go ahead and start substituting values into that function. We want to know what the dollar amount is after 7 years, so we're trying to find A of 7. And so we'd say that equals 1,000 times 1 plus r. Now when we do the interest rate, we don't put a 5 in there. We think of the percentage. It's 5 over 100, right? So it's really 0.05. And so inside here will be 1.05. That's a real important thing to remember when you're calculating these problems. Put that percentage in as a fraction, not just the number part. Think of it as 5 over 100 or a decimal 0.05. And then you raise that to the 7th power. Okay? So just like we did on the previous problem, we do that 1.05 to the 7 first. And so go ahead and do that on your calculator and then multiply that by 1,000. And we're dealing with money here, so we want to write our answer to 2 decimal places. And so we would end up with $1,407.10. Put a dollar sign out front. So that's our answer there, $1,407.10. So exponential functions, those can be used to study growth when populations are doubling or tripling over a certain amount of time, and also to study how money accumulates interest. Next, let's talk about graphing these exponential functions. I'll show you what they look like, and then we'll also do one on a graphing calculator so you can see how to do one on a graphing calculator. Now, if you're graphing an exponential function of the form that I have in the middle there, a to the x, they take on different shapes depending on the value of a. Like on the left one, what I'm going to do is graph a function that a is between 0 and 1. So that means like a fraction, like a 1/5 or a 1/4 or something like that. When a is between 0 and 1, the graph tends to have this shape right here. And it's interesting that they will always go through the point 0, 1 right there. They'll always go through that point, no matter what their shape is. Now, the smaller the fraction is, the steeper that graph will be. So, like a 1/8, if that graph I just drew was a 1/4, if a was 1/4, 1/8 would be even steeper. It would be like that, going through 0, 1. Now, think about why they always go through 0, 1. Because that at that point, x would be 0, and anything to the power of 0 equals 1. So they always go through that point. Likewise, when a is greater than 1, what happens here is you get a curve like this, going up to the right instead of going down when it goes to the right. They also go through 0, 1 as well. And the larger the value of a, the steeper the function's shape is. Now we don't have 1 for when a equals 1, because just think of that. If a equaled 1, 1 to any power will still equal 1. It'll just be a horizontal line through y equals 1. Let's go ahead and do a practice problem. Let's graph y equals 2 to the x. And we'll do that on an xy coordinate system first. Let's make an xy table, and then I'll show you how to do it on a graphing calculator. And you can always use a graphing calculator to check your work. So y equals 2 to the x. Let's make an xy table. And let's choose a few values for x. Let's use -2, -1, 0, 1, and 2. So when x is a -2, we would have 2 to the -2 power, or 1 over 2 squared, which would be 1 over 4. So y would be 1/4. Then when x is -1, we'd have 2 to the -1, or 1 over 2 to the +1, which is just 1/2. When x is 0, y is 1. When x is 1, y would be 2 to the 1, or 2. And then we'd have 2 to the 2, or 4, for an answer there when x equals 2. Let's make an xy axis. Put some tick marks on there. And let's go ahead and graph this. We'll plot our points first. When x is a -2, y is equal to 1/4. So that's a really small number there. When x is -1, y is 1/2, so about right there. Then 0 and 1. And then when x is 1, y is 2. When x is 2, y is 4. And so we can see that exponential pattern developing there. We just draw a line through those points, connecting the dots. And we never go beneath the x-axis, because it'll just get smaller and smaller and smaller. The more negative it gets, the closer it gets to 0, but it will never equal 0. And so we just draw it right along that horizontal axis. Now let's check our work by looking at a graphing calculator and seeing how to make an exponential function and graph it on a graphing calculator. The first thing we would want to do if we're using a TI-83 Plus is go to Window and press that Window key there, and then go ahead and type in some values for x min, x max, x scale, y min, y max, y scale. What that's doing is that's setting up your graph. X min, that means your graph would go to the left 10, x max means to the right 10, and then the x scale, that means that's how far apart your tick marks would be spaced. So we'd space them 1 apart. And you can design whatever kind of graph you want. And so for this one, we can just do it pretty simply with a min of -10, a max of +10. I just chose those numbers so I would have enough points to see everything that I wanted to see. And then y min and y max and y scale. And then the x resolution, I usually just leave that as 1. Next, what we would do is go to the y equals button there at the top left corner, and you press that and you type in your function, 2 to the exponent of x. And the way you type in the x is, hopefully you can see my cursor here, x t theta n, that symbol right there, you just press that and that puts the x on there for you. So you type in your 2, the exponent key, then hit this button here where it says link above it. That will put your x variable on for you. Then you can hit either trace or graph. I hit trace, and you can see that little x cursor there, and what you can do is you can move that thing around using these arrows, and it will tell you what position you are at on the graph. For example, see this x equals 0 and y equals 1. That's where that little x cursor is right now. It's at that point. And you can move it around anywhere you want on this line, and it'll tell you your xy value for that particular place. And so you can see on our graph here we have tick marks. They go out to +10 and then -10, and then on the y-axis down to 10 and up to 10, just like we had set it to do. And the shape of our function, it looks like the one that we just drew, so that gives us confidence that we did graph that function correctly. That's what we use the graphing calculator for, is to check our work, not just to figure out what the function is, because that's just really easy. All you do is hit 2 chevron mark X and then hit graph, and you know what it looks like. There's really not a lot of thinking involved. You have to set up an XY table and put in some values and find out what the corresponding Y values are for those. Plot it and draw it yourself. That really helps you understand what that exponential relationship is like. Okay, well that's all for lesson 114.